Hello, my name is Cody Caston. My team is Aaron Griffith and Christian San Ramon, and we're doing our first presentation on cryptography. Just a quick overview of what we'll talk about today. The first, of course, is what cryptography is and a brief history of cryptography. And then we'll jump a little bit more into what makes up cryptography. So encryption, symmetric versus asymmetric, hashing, adding salts to those hashes, digital signatures, and then different cryptography attacks that we commonly see within the cybersecurity world, brute force, man in the middle, the mathematical attacks, and then password cracking. So cryptography is a method of using advanced mathematical principles and storing and transmitting data in a particular form so that only those whom it is intended can read and process it. Major goals of cryptography, of course, is confidentiality, authenticity, and integrity. Those are the main goals of not only cryptography, but of cybersecurity in general. So we see a lot of the intertwined definitions and goals between cryptography and cybersecurity. One thing to note, of course, is it's continuously evolving to ensure security is not compromised. As we've all seen, information systems capabilities continue to grow at an alarmingly fast rate. So that means all of those cyber criminals out there are learning at an alarmingly fast rate, and they are learning how to break these things. So we have to continuously evolve our techniques and our algorithms to ensure that we are maintaining security moving forward. A brief history of cryptography. It is found in the first use case was found in non-standard hieroglyphics carved into the wall in ancient Egypt. This was not a serious attempt at security or secrecy. Basically, people just wanted to use it, or the individuals wanted to use it as kind of an amusement thing. They just wanted to see if onlookers could crack the code or understand what was being said, and it wasn't anything like we've seen today. The first use case that is really tied and pretty common to what we see today is the Caesar cipher. It is an encryption method that was first used by Julius Caesar for his private correspondence among his officials. So as you can see here on the right, it was a very simple code that could be cracked. All they did was realign the letters of the alphabet with other letters. So in this case, you see the D would then be aligned to an A. So if it was a D in the code of the message, that would be aligned to the A, E would be B, and then F would be C. So it was really very, very simple to crack. But at that point, not anybody really knew what was going on with it. So it's probably a pretty secure way at first until someone was able to crack it. So as technology has evolved, so have the cryptographic techniques incorporating mathematical algorithms, making them nearly impossible to crack. So of course, nothing is impossible, definitely when you're talking about cybersecurity and information system capabilities. But the mathematical algorithms involved in encryption and in hashing and those things, of course, that we'll address later on are very, very, very hard to crack, and it takes a very competent person. So again, like I said earlier, cybersecurity and cryptography are pretty much intertwined, and they have the same goals, the same fundamentals. So the first is authorization, applying limits and controls to ensure only those with authorized access can access. We want to make sure that people that don't need to see something aren't seeing it. It's about as simple as that. Authentication kind of ties back in with that. So it's confirming who you say you are by checking the provided credentials against stored ones. Integrity is assurance that data can only be accessed and modified by authorized users. And then, of course, identification, which we've seen recently with the uptick of multi-factor authentication, is proving who you are, who you say you are is who you are. So basically, with the multi-factor authentication, you can have a weak password, but with that second layer of security, you're helping with identifying who you are. So they all have the same fundamentals. They all have the same goals as far as securing data, but they all work hand in hand. In cybersecurity is very tough. It's hard to ensure all of these are being attained.
All right, hello everyone. My name is Christian, and I will be teaching you about encryption. So building off of what Cody has already taught you guys about cryptography, which uses a lot of mathematical functions and formulas to obfuscate different types of data and protect encryption is just building off of that. So it's primarily used for encrypting partitions and different disk types on physical machines, but it's also used for communication between servers and browsers, or really any type of communication uh, that is going across the internet. So some of these protocols are SSL, SSH, HTTPS, um, and if you're sending anything sensitive, I know in the government they have confidential information, or just anything that you don't want someone to see, you can encrypt it. So this is passwords, payment information, and basically what it's doing is it's encoding your initial data or your strings, and then once you send it off, um, and then your recipient receives the message, they can then decode it using a key, which I'll later discuss. And then someone in the middle wouldn't be able to see what the contents are or read the original message. So it's very, very important for data security. So how encryption works. So for your plain text, this is what you are inputting into the encryption. So this is either your message or just the data on your hard drive. You use a key and then send it through the encryption algorithm, and then it spits out ciphertext, which is non-human readable. It just looks like a bunch of random characters. So this is what would be, if intercepted, this is what the eavesdropper would see. And then once it gets over to its recipient, they use their key and send it through the decryption algorithm, and then they get the original message that they would have seen in the beginning. So decryption is just the inverse of encryption. So there are two different types of encryption. There's symmetric and then there's asymmetric encryption. So first I'll be discussing symmetric encryption. And what this is just the same key is being used during encryption and decryption, which means the sender and the receiver both have the same key. So this key is known as the secret key, since only these two know what the key is. So the most common algorithm used is AES, and this is Advanced Encryption Standard, and I'll discuss this later in more detail. So symmetric encryption, it's much faster than asymmetric, and it supports confidentiality, but it does not support authentication or non-repudiation, which Cody discussed earlier. So there are two different types of blocks in how the actual algorithm works. So how does symmetric encryption work? So it's very similar to the first slide that I showed you, but you have your input, and this is your plaintext, and you use your shared key, which both the sender and the recipient have, which they've already shared before this. So you feed it into the encryption algorithm using your key, and then it becomes the ciphertext, which is just a bunch of jumbled mess. And then then it goes into this should be decryption algorithm, and the recipient uses your shared key to decrypt the information, getting the original message. So there are some advantages. It only requires one key, but this, on the flip side, unique key management, it can be a pain to have to manage several of these unique keys if you're sending encrypted files back and forth between several different people. So it's relatively fast, and it is difficult to break if the larger key size is used, which I'll discuss in the next slide. But the main drawback is key delivery, which you have to get the shared key from the sender to the recipient somehow, and if you just email it over, then you're risking getting it intercepted, and if someone intercepts it, then they can decrypt all of the files that you're sending. So basically defeats the purpose. All right, so Advanced Encryption Standards, also known as AES, one of the more popular symmetric encryption algorithms, can be a 128, 192, or 256 bit long key. And this is just the output of the key, which is kind of your key to unlock whatever the contents are. So as the values get higher, it becomes more secure. So 256 is more secure than 128. So it utilizes block ciphers, and it's used in disk partition encryption, VPNs, which is anonymizing your web traffic and making it more secure. And then also Grand Theft Auto, I guess it's utilized to prevent hackers from hacking multiplayer gameplay. So 128-bit key would take billions of years to crack using a brute force attack, which we'll discuss later, or which we'll explain later. But so it's relatively secure. Is very secure. There's some vulnerabilities, and like I mentioned earlier, just a man-in-the-middle attack, intercepting the password, and then there are these other attacks called side-channel attacks, which I'll explain later on in the presentation. And then this is kind of just how the algorithm works. You have the plain text and then the secret key, and they lead into the cipher and then the cipher text. Alright, so on to asymmetric encryption. So this is known as public key cryptography, and in this method there are two different keys, one used in encryption and then one used in decryption. So these keys are assigned to one person and they're mathematically related. So I would have two keys, and I would have my private key, which I know and no one else knows, but then there would also be a public key which is out on a server which everyone has access to, and if they want to send me a message, then they'll use my public key when they're encrypting the message, and I'll explain this later in a diagram. I think it's a lot easier to understand encryption with the visual aids as well. So the most common algorithms used in asymmetric are RSA, elliptical curve, and digital signatures, which is what Cody will be discussing. And asymmetric encryption is a little bit slower. It's quite a bit slower than symmetric, but it does support, this should be symmetric, but it does support authentication and non-repudiation. So the time sacrifice is worth it if you want more security. So how asymmetric encryption works, like I mentioned, so it just depends on who's sending the messages, but typically the person receiving they have their two keys, and then so this is me over here, and then this is Cody. So I have my secret key, which I only know this, and then I have my public key, which I have sent out to a public server and told Cody where he can access this. So when Cody wants to send me specifically a message, an encrypted message, he has his data or his message, and he goes into the encryption algorithm and uses my public key. Then it spits out the ciphertext, and when I receive the message, I use my secret key, which is decrypt the message, and then I can see the original contents. So the advantages: key management. Obviously, you only have to know what it's easier to keep track of your one secret key. It's more scalable. I mean, one public key to more than 1,000 users. which anyone could use that wants to send you a message. And it supports authentication and non-repudiation. So the disadvantage, it's a little bit slow, and the size is limited. So another drawback is you're not able to see who is sending you, or to confirm the identity of the person sending you the message. And this is where digital signatures come into play, which Cody will be discussing.
Hi, this is Aaron. I'll be presenting hashing. Hashing is a method of cryptography that converts any form of data into a unique string of text. A hash can be performed on various types of files, including text, audio, video, or a program. The results will be a string of numbers unique to that file. Two common types of hash values are MD5 and SHA-1. I'm hearing that the MD5 hash is broken, so I'll only show an example of the SHA-1 hash. So I created two text files, one titled test1, one titled test2. So to get their hash value, I open up Windows PowerShell and I write this script: get-file hash, then the path to my test1 file, then -algorithm SHA-1. That script populates this hash value. And so this hash value is like a digital fingerprint for the test1 file. So I did the same thing, wrote the same script, just replaced test1 with test2, and now you can see we got an entirely different hash value. So now that hash value is like a digital fingerprint for the test2 file. So to verify the hash, I rewrote the code, get-file hash, the same script that I wrote on the first script for test1, and I got the hash value that starts 99EA, which is exactly the same as the one we got up here. So they match. I did the same thing again for test2, and again, this hash matches this hash right here. So now we can verify that those are the hash values for a test1 file and the test2 file. So those are the digital fingerprints for those files. So although hashing is a form of encryption, it's primarily used for comparison purposes. For example, in the digital forensics field, a forensics examiner will review their evidence file first and find their hash value. Then at conclusion of their investigation, they'll obtain the hash value of the file once again. If the two hash values match, then the forensic examiner can be sure that they did not alter the file. If the hash values do not match, then the examiner altered the file and the evidence is now corrupt. Another way hashing is used for comparison is while downloading software. Some developers provide the hash value of their software, so you can compare the value they provide with the hash value of the version you're trying to download to ensure that you're downloading not only the correct file but also a safe file. So a way you can enhance the security of a hash is by adding salt. Salting combines a password with salt, then hashes that string. Salt is a random string that is added to the end of your password for the purpose of enhanced security. By adding salt, you prevent hackers from performing brute force attacks or SQL injection. Now, as an extra layer of security, you can also try peppering. Peppering is very similar to salting. However, rather than adding a random string to the password, a pepper is not random. It is usually a hard-coded string that an entire organization will use. Now, if a hacker were to try to brute force attack this hash, they would have to discover the value of the password, the salt, and the pepper. So this is an example of salting and peppering. The first example, you'll see that we have the password, which is let me in, a length of 8 salt, so we have 8 random characters, and then when we add the password with the salt, it'll look like that. And then now, instead of just hashing the password, we hash this value, which gives us this hash. So an example of peppering is we'll have the same password, we'll have the same salt, except now we're saying as an organization, U&M will have a pepper that is U and M. So now their password, salt and pepper, will include the salt right here, the password, and then the pepper, which produces an entirely different hash. So why would a business do this? Because it's really unsafe to store plain text passwords in a database. If a database is compromised, all of the user passwords are compromised. So businesses should store the hashes of the user passwords so they are not compromised in a data breach. Cryptography can be broken through various attack methods such as birthday attacks, mathematical, brute force attacks, man-in-the-middle, dictionary, replay, or SSL or TLS downgrade. We'll explain a few of these attack methods. A brute force attack is a trial and error attack method in which an automated program guesses every possible combination of passwords. A brute force attack is basically breaking down a door to get to a password. This kind of attack works really well when someone has a weak password. In this case, the program will crack passwords very quickly. If the password is more complicated, then it could take the password cracker more time, or the program will not be able to crack the password at all. An option is to use a table of common passwords. An attacker will search for common passwords such as password, first name, last name, date of birth, etc. You can catch a brute force attack by looking at logs in tools similar to Splunk, where you can track when unsuccessful logins occur. If you have thousands of unsuccessful logins in minimal time, that is more than likely a brute force attack. To stay safe from brute force attacks, use passwords that do not include names, relevant dates, or any words in general. Try using a combination of random numbers, letters, and symbols at a long length.
Another core component of cryptography is a digital signature. It's basically an electronic encrypted stamp of authentication on digital information, such as messages, softwares, or any sort of digital document that confirms the integrity and authenticity of that message. The signature ensures that information originated from the signer and was not altered, which proves the identity of the organization that created the digital signature. Any change made to the signed data invalidates the whole signature, therefore making that piece of information unusable or invalid. There's plenty of softwares that you can use out here that you can purchase, but you can also create your own digital signature algorithm depending on your abilities. As you can see here, there's a picture of how it all works. If anything within that line or lineage of how this message is originated and created and then sent is altered, therefore, like I said above, your message will then not be valid. One of the more common attacks that we see is the man-in-the-middle attack, which is when a malicious third-party actor acts as a middleman between server and end user. So as you can see in the picture to the right here, there is one individual trying to communicate with another. However, there's someone in the middle of that is able to first receive the traffic. They can then manipulate it, do whatever they want, and then send it off to the intended destination. At that point, you have no idea if the information has been manipulated, have no idea if the information that was sent is actually the information that you received. So, at first it was very hard to detect, but a commonly used public key encryption is used to exclusively combat this kind of attack. It really does help ensure that the third party actor is not able to manipulate the information that they receive because they can't decrypt it. You encrypt it, you send it over, they decrypt it, then you encrypt it, you send it back over and decrypt it. So that third party individual will then not be able to do anything with the information that was received.
Alright, so on to mathematical attacks. So what this attack is designed to do is to attack the properties of an algorithm using mathematical computations. So there are five different categories, and all of these depend on the type of data that you're able to gather. So the ciphertext only, the attacker has the ciphertext of several messages that are encrypted with the same encryption algorithm, but no access to the plain text. So this is the most difficult method to crack because you have just one piece of the puzzle, and you're trying to determine what the encryption key is. So getting the ciphertext is usually pretty easy using Wireshark or TCP dump, but it's pretty hard to figure out what the key is because you don't know which algorithm was used to encrypt. So in the next, known plaintext, attackers have messages in both encrypted and decrypted form. So it's a little bit easier than the ciphertext attack, just because the plaintext can be examined. But attackers can actually reverse engineer some of these. So then on to the chosen plaintext, which is quite a bit easier. Attackers have access to the plaintext and the ciphertext and can choose which messages to encrypt. It's quite a bit easier to determine the key. And then onto the chosen ciphertext, which attackers have access to the ciphertext that is to be decrypted and resulting in the plaintext. So then the side channel attack, which I mentioned earlier, this is aimed towards analyzing the hardware used for these crypto operations. So some of the things that you'd look at in a side channel attack would be the operating temperature or the computation times, electromagnetic emissions, vibrations, and even reflections off users' eyes. So obviously you would have to have be in close proximity to this crypto hardware, analyzing the operating temperatures at the computation times to look at if the operating temperature is rising, then most likely the computer is working hard or it's taking longer, which could lead you to believe that it's an asymmetric algorithm that's being used to encrypt or decrypt. And this just subtle little characteristics can just give some more insight to these experienced hackers who are more familiar with all of these different characteristics that help them to figure out which encryption algorithm is being used, and if you know that it's just another piece of the puzzle that you can use to determine what the key is.